Hello, and welcome to today's webinar, Using the RISA-Revit Link for Concrete. I'm Matt Brown, and today I'm going to be demonstrating to you how to use the RISA-Revit Link to communicate between RISA Floor, RISA 3D, RISA Foundation, and of course Revit. Now that can be either Revit or Revit Structure. Either way, we're going to be using the structural components within Revit to do this. So the RISA-Revit Link acts as a go-between between the RISA programs and Revit, and the RISA-Revit Link is available as a free download from our website, risa.com. For an outline of what we're going to be doing today, as you can see, we're going to be starting a model in Revit. Now you can start a model in Revit or you can start one in RISA. The RISA-Revit Link allows you to go either way with that. However, in today's example, we're going to assume that a Revit model has already been built and that we want to get analysis on this Revit model. So once we start with Revit, we're going to send it out to RISA Floor and get our analysis and design, maybe make some changes along the way, and then bring it back into Revit. That process is called round tripping. Then, once it's back in Revit, we'll make some more changes and then perform a second round trip so that you can see how multiple steps through the process are able to get our information synced up between the RISA model and the Revit model. So the first part that we're going to deal with here is going to be starting in Revit. Here I have a Revit model, and I have this model created in Revit 2016. And so what we can do with this model is take a look at what's been created here. Now bear in mind in Revit that there's always a physical model and an analytical model. So if I zoom in here, what we'll see is that this tube brace, for example, has a physical component, which is actually the tube itself, and then you'll see a little colored line on here. It's sort of a yellow line, might be difficult to see. That's the analytical element. So if we come in here and switch this over to a wireframe, we might be able to see it more clearly. So every element within RISA, or within Revit, has both a physical component and an analytical component, and this allows you to have slight differences between how the elements are aligned for analysis versus what you physically want to show on the drawings in Revit. So we can take a look over here under the 3D views and take a look at the analytical model view. So this is sort of a simplistic view that shows us how RISA is going to interpret how all these elements connect with each other just using basic stick figures. Now what we have for this building is it's a multi-story building, and it's mainly composed out of concrete. So in this case I've got two separate mat slabs for foundations down here, and then some individual spread footings. And what I have at these two floors is a two-way concrete slab. So you'll note that there's no beams at all supporting that floor. It's just a slab that spans from column to column and maybe from some walls. And then up on the roof here, we have a steel frame with some braces. So this model is a mixture of materials which is well supported between RISA and Revit. Now before we go ahead and export this model out to RISA, we do want to take a look at a couple things in here. Number one, you always want to review your analytical model very closely in Revit. So this is something that most people don't often do, and it's the source of a lot of trouble when linking between the programs. Essentially, if we take a look here, we want to make sure that all these stick pieces line up with each other. In a lot of cases, when you're busy modeling the physical model within Revit, you're going to ignore this, and then you're going to come in and find out that this brace maybe doesn't actually connect to the beam in the column, that it falls short. This is something that Revit wouldn't be concerned about, but RISA definitely has concerns with. So we need to make sure, above all, that before we do any importing or exporting, that everything is perfectly aligned with the analytical model. So you want to go over that with a fine-tooth comb. Once you're satisfied with that, another thing that you're going to want to take a look at is something that we've discovered is actually the source of a lot of confusion and problems with the RISA-Revit Link, and that's the Revit merge tolerances. So within Revit, if you go up to the structure menu here, within the structure group, there's a little arrow right here at the bottom right corner of that group. That'll open up these structural settings. And if I pull that open, we can go to the analytical model settings. And what we find under analytical model settings here is that we have tolerances. Now these are the default tolerances that I have here that Revit ships with. Essentially they're all 1 foot except for this one, which is 6 inches. So what do these tolerances mean? This means that if one node or one element comes within a foot of another node or element within the Revit model, these are considered snapped together and joined. And while it's good to have some sort of a tolerance, I mean, certainly we don't want to have to get down to whether or not a beam is within 1/64 of an inch of girder that's supposed to support it, these tolerances are grossly oversized by default. So what you end up with is problems where when you have tight framing together, when things come within a foot of each other, the program just starts snapping it all together. And it's been proven to cause a lot of issues with the transfer back and forth between the RISA-Revit Link. So one thing that I always recommend doing in your Revit model before you do any transferring back and forth, or even in fact if you're starting with a blank Revit model and you haven't imported from RISA yet, is that you need to set these tolerances to appropriate values. Now in this case, I've found in practice that 1 inch is a rather reasonable tolerance as opposed to 1 foot. So what I'm going to do is come into all of these settings here and change them from 1 foot to 1 inch. And I'll hit OK. And what this is going to do now is it's going to go in and readjust the analytical model within Revit to make it actually extend correctly and sort of redo how everything works so things don't get automatically snapped together all the time. Alright, so with that set, we're now going to be ready to do our initial export out to RISA Floor. So what we're going into now is part 2, exporting to RISA Floor. So within Revit, if I come up here to the Add-ins tab, if I have the Risa-Revit link installed, we'll see that we have a Export to RISA button available, as well as an Import from RISA and a RISA Parameters button. So this will allow us to import and export from RISA. RISA Parameters allows us to control certain properties of elements within Revit that the Risa-Revit link will care about, and we'll take a look at that in a moment. Now if I go to Export to RISA here, you're going to see this dialog that has a number of different options in it. So first off, we can control which version of RISA we want to go to, whether it's RISA Floor or RISA 3D. If RISA Floor is available, if you have that installed, that's usually the better choice because oftentimes the RISA Floor has more capabilities that we can use that'll be similar to what Revit has. So we have a tighter link between RISA Floor and Revit than we do between RISA 3D and Revit. But RISA 3D is always an option, and of course if you don't have RISA Floor, it'll be your only option. So coming into here, you can see there's a couple of options to launch the program automatically to export selected items. Let's take a look at some of our other options before we export here. So we can control whether the coordinates in the Revit model are going to be the project base point or the survey base point. So in this case, we're going to use the project base point from the Revit model to set what the coordinates are in the RISA model. We can set whether or not the Revit Project North or True North will be exported to RISA. Once again, Project North will be fine. We can control whether we want to take the Revit Physical Model or Analytical Model. This option is only available for RISA Floor. And in this case, we'll take the physical model since there's certain floor-to-floor information that's been set up in there. But there's other circumstances where the analytical model may be a better choice, and that's been covered in other RISA to Revit webinars. And then if we come down here to the RISA Floor Design method, we can either optimize all of the sizes from this model, or we can just take the existing sizes from the Revit model and simply perform an analysis on them in RISA Floor without optimizing them or changing them. That's especially useful if you've got everything sort of locked in for your design and you're only making minor changes where you don't want to wholesale be changing a lot of column and beam sizes. In terms of the elements that we want to link with Revit and RISA, we have the walls, boundary conditions, footings, which requires that you have RISA foundation, project grids that's currently supported for orthogonal and rectangular grid systems, although a upcoming grid overhaul in RISA will be able to allow you to do more with that. Diaphragms, and that would be for the beam supported floor systems here. Loads and load combinations, you'll note, are unchecked in here. The loads and load combinations don't always map over perfectly due to certain limitations or differences between how RISA and Revit are done. Typically, we do not recommend sending these over unless you have a very explicit reason why you want to get your loads into Revit. And then we have foundation slabs. This requires RISA foundation. And elevated slabs, this requires that you have RISA floor ES. So with these options chosen on here, I'm going to come down and set up an Exchange file where we can import and export this to. So I'm going to find a folder that's going to be available to me on here, and I am going to create an Exchange file in that folder. It'll automatically set up a new RISA model file name, and then I'm going to hit OK on this. And so what's happening now is the program is performing a verification, and we get this warning that pops up from the RISA-Revit Link verifier. And what this says here is that the export failed. There was no match found for top level parameter. So what this warning is all about is basically saying that certain columns that we have in the model have no top level associated with them, and so we can't bring those columns out. So as opposed to hitting ignore, this verifier allows us to hit cancel, which basically cancels the export and allows us to go in and take a look at what's going wrong here. So within the Revit model, if I come back and click on one of these columns, like let's say the steel column here, I can see that the base level for this steel column is the 3rd floor and the top level is the roof. So that should be fine. But if I come into the elevation of the building here, we can take a look at the levels that have been assigned to this Revit model. And what I can see here is I have a 3rd floor and roof, so everything should be fine here. Now I'm going to click on the roof here, and let's make sure that our RISA parameters are turned on. So what we can do is, currently these RISA parameters are off. I'm going to click this button that was under the Add-ins tab to turn the RISA parameters on. And over here on the left under Properties, we can see a couple of properties. One of them is RISA Structural Floor, and one of them is RISA Elevated Slab. Now this RISA Structural Floor setting allows us to control whether or not this level from the Revit model should be exported out to RISA. And we can see that that is unchecked. In other words, the RISA-Revit link, with the Revit model set up as it currently is, will totally ignore this roof level. Well, we don't want that to happen, so we want to check that box. At the same time, there's the RISA Elevated Slab option, and that controls whether or not this floor should be exported as a two-way slab floor or as a beam-supported floor. Now in this case, for the steel roof that we have, we want that as a beam-supported floor. In other words, the metal deck will be supported directly by the beams. If we go down to the 3rd floor, we want that floor to be exported to RISA as well, but we also want the RISA Elevated Slab box checked, since this is a two-way elevated slab. On the 2nd floor, we can see that the elevated slab box is unchecked, so we want to make sure to check that so that that floor gets correctly exported. And then if we go down to the ground here, we actually want this ground level where the foundation is to be unchecked for RISA Structural Floor. What's going to happen is, if we check that as a structural floor, the program's going to interpret this as another elevated floor above ground, whereas we really want this to be a foundation. And we can indirectly have the program consider it as a foundation by having it be the first level below a RISA structural floor that does not have that RISA structural floor box checked. So it will be interpreted that way. So now that we've corrected those parameters, we should be able to export this without problems at this point. So I'm going to go back into Export, and I'm going to go back and make sure that our Exchange file is pointing to the correct location. And then I'm going to double check all my settings, and I want to bring over everything except for loads and load combinations. And then I'm going to hit OK on this. And so what we get now is it runs through the verification, and then it's coming out here and actually creating that RISA model from scratch. And we get a little summary here showing everything that was created. I'll hit OK on that, and now RISA Floor is launching. Once RISA Floor finishes launching, we're going to be able to come in and begin modifying this, because there's certain settings from this that are going to need to be adjusted. So we now have RISA Floor pulled up here, and in RISA Floor I want to come in here and go to the Model Settings, or Global Parameters. And in the Model Settings, what we can do is go to the Codes tab and take a look at how this model is going to be designed. So this model consists of steel and concrete. Now concrete is designed using an LRFD type method, so it's going to have the factored loads. It would be a lengthier process for us to do the steel as ASD in this case, because we would have to set up two different sets of load combinations, one for steel and one for concrete. So to save time on that, I'm going to set the steel to be LRFD so that the concrete and steel can both share the same load combinations. Next, I'm going to come in here and go to the Wind tab, and we can set up ahead of time how RISA 3D will generate the wind loads for this model. And so in this case, what I want to do is set this to be the ASCE 710, and we'll assume that this building is in some place like, say, South Florida, where wind is going to be a big deal and seismic won't really matter. So I'm going to set the wind speed to be 180 miles an hour, and we'll set this for exposure category D, so we'll assume it's right on the coastline. Then I'm going to come over to the Seismic tab, and let's say that by inspection seismic will not control in this building. Maybe it's a seismic design category A, and so I'm going to set the seismic code to none so that we don't bother generating all these extra seismic loads that we don't really need. I'll hit OK with that, and we can see here that we're at the roof level, and so it's brought over all that framing and the deck from the roof. And I can come up here to see what kind of deck that we brought over from Revit. And what we'll see is it's this pink deck, and from the deck definitions, we'll be able to see that's called the 1.5-inch metal roof deck. Well, I'm going to set up a different roof deck for this one. I'm going to come up here to this metal deck definition, and let's come into the database and pick out a Vulcraft deck, and we'll do a Type B deck, 20 gauge. We'll say the deck braces the beams every 2 feet on center, and then it can span up to 5 feet. So the program will give us a warning if it spans farther than that. And then what I'm going to do is assign that metal deck to this floor system. So I'll come up here to modify the existing deck and tell it to use this type metal deck instead. So we've put that on there. And then I also want to make sure that the default deck for the roof is also metal deck, which I can do through the floors spreadsheet. So I'll come up here and change the deck default to metal deck. Next, we also want to change the beams and columns in here wherever we have a bracing system so that those can get a lateral design on them. And so I need to come up here and select only the frames which contain brace frames in this model. So I'm grabbing those right here. Now this is something that I could have set up ahead of time in the Revit model as well, but just to demonstrate how things typically work out, usually you'll forget to do that in the Revit model until you get over here. And so you can always make that change in RISA instead. But there is a lateral setting for the framing within Revit. So I'm going to come up here and change those columns to lateral. And I'm going to go into the Modify Beams and say that the beams also should be lateral. So now I've modified both of those. And the braces would have come over from Revit, but they'll be on the RISA 3D model that's embedded underneath this RISA floor model. The next thing I want to do is set a column design list. So I'm going to come into the columns here, and we'll see for the roof that for the steel columns on the roof, they're all set to shape wide flange. This means that the program will optimize these to any size of wide flange. But what I actually want to do is ensure that these columns get designed as nominally 10-inch wide flange members. So we can see that the code for that is WF10. So I want to fill in all of the rest of these, and I'll use the fill block command to put them all as WF10 shape types. So we've got that set. The next thing that we want to do is make sure that all these columns are getting pinned to the concrete slab below them so that we don't have to detail out all the base plates to take moment. And you'll see right now the splice type for this roof is called default moment. So to change the default splice type, we do that from the floors spreadsheet, and I can come in here and say shear, and so now the splice at the bottom of these columns, and that would be the splice between the steel and the concrete, will be a shear splice as opposed to a moment splice. So that'll help out with the detailing. Now you'll also note that we have a material on here, steel ASTM A992. Well, if I go to the materials spreadsheet, you'll see that a lot of materials from Revit got brought over, including this steel ASTM A992, and it has slightly different properties from what the default properties are in Revit. In fact, certain properties like the RY and RT value are incorrect. And so what we want to do is, rather than using this Revit material, let's use the RISA material that's already been set up with the correct values, the A992. And so note that this is all just text, so you may glance over this and see, oh, it says steel ASTM A992. Bear in mind that that is a Revit material that's totally different from the RISA material, just quote A992. So I'm going to come to the material here in the spreadsheet, and I'm going to do a fill block to call all of that the A992 material. Next, let's set up the slab definitions. So that would be for the, one other thing, for the beams, we're also going to want to come in and change the beams up here as well to that standard A992 material. Now we'll move down to one of the concrete slab floors. So we see on this floor level here, this green outline shows us that two-way elevated slab, and then we have these columns inside of here. Now to change how the slab is done, we need to go into these slab definitions. And so we can see in here, for the slab definition, that we have a material assigned, which is a concrete cast-in-place gray. Once again, when you see these very wordy material descriptions, those are coming out of Revit, and of course we don't really care what color the material is. In this case, let's go with the material that's from RISA that has some properties that we know are going to work out well for us, the Conc 4000 NW, which is a 4000 psi normal weight concrete. For the reinforcement design, we want to do a two-way analysis as opposed to a one-way analysis on this slab. And for the diaphragm that gets created from this, we can choose semi-rigid or rigid. Let's assume in this case that with a 10-inch thick concrete slab that rigid will be fine. And that's going to allow us to speed up our analysis so we can get back to the round tripping that much faster. I'll now close out of the slab definitions and take a look at both of the slabs to make sure that they're set up on that definition, which they are, so that's good. The next thing I want to do is change the area loads. And so I'm going to come in here to the area load definitions, and we see that we have a load set up for office, which is 10 PSF dead and 50 PSF live. And another load that's set up for the roof, which is 10 PSF dead and 20 PSF live. Well, I'm going to come into the floors spreadsheet and set up the default area load for the roof to be a roof type load, and for the second and third floors to be an office type load. That means that that load will be used unless otherwise specified on those floor levels. The next thing I want to do is go in and make sure that the concrete materials are otherwise set up correctly in the model. So I'm going to go to the wall panels spreadsheet where we can take a look at the walls that were brought in. Once again, we see those are using that Revit concrete cast in place gray, where we actually want them to use the concrete 4000 NW. So I'm going to set that in there. And let's take a look at the columns spreadsheet as well. Once again, we want that material to be the concrete 4000 NW for all those columns. Now for the shape type, this is set to rectangular for all these columns, but what I'd actually like to do is get a square design for the columns, and we have a design list available for these called rectangular square. So what I can do is set that for all of these columns to be rectangular square, and now we'll get a square design on those instead. And you can see that these changes all came down to the second floor as well, since there's no splice between the third floor and the second floor. So if I change it on one, it changes them on both. Alright, so with all of that set up, the next thing that we can do is draw in our support lines for our RISA floor slab. So this would be for getting the two-way concrete slab design. So I'm going to come in here under support lines. Now note that this requires RISA Floor ES to be able to do. The regular RISA Floor does not have the two-way concrete slab design in it. And we want to set up support lines, which are basically going to be used to create design strips where we can get our design for the rebar in the slab. So we're going to want to set that up relatively orthogonally. So we're going to pick out these north-south strips. And I'm just going to draw in here some lines that indicate a sort of shortest path between supports. And these lines can cantilever out to a slab edge as well. So I'm going to sort of cantilever that one out. And so as I click on here, these lines are going to be used to create the column strips and the middle strips that are used for reinforcement design in a two-way concrete slab. So I'll run these right up across here. And we'll do this only for one floor in this case, although we could do it for all of the floors in the structure. right here we can see actually it makes sense to have the support line skew a little bit so that it can go from that wall to that column, since the slab will really be spanning between those 2 points. So with the vertical strips now drawn, next I'm going to come in and do the horizontal ones. These would be the east-west rebar. So we'll come down here and draw the east-west rebar into the nearest supports. Right there. We can get it across between these columns and this skewed wall. Now you'll note that this building is not set up with a very regular structure type, and that's actually on purpose just to demonstrate that you don't always have these sort of perfect little rectangular buildings in real life, especially where architects are involved. So oftentimes you have to know how to be able to handle unusual situations like this. And so this model sort of gives a little demonstration of how we could get a two-way concrete slab design on something other than just a normal rectangular box. Alright, so we're just about done setting up those design strips across here, and the support lines are now all drawn. And then what we do is tell the program to generate the design strips. So I click this Generate Strips button over here. And so let's take a look at the north-south design strips here. And so what we can see is that I've got some overlapping. Oftentimes, when we've got a little bit of a skew or things like that, we need to come in and modify some of these edges. So I'm going to use this Edge Align tool to get these design strips sort of lined up with each other better. Now, we want to watch out to make sure there's not any huge gaps of white space in here, because of course those locations are going to be locations where we're not going to get any design for the forces in there. So we want to try to make sure that our design strips cover as much slab area as possible. So now that I've got the north-south strips set up, let's come back into the east-west strips and also get those ones aligned. And so I will align some of these with locations where they make the most sense anyhow. Down along there. And we'll fix a couple more of these. So oftentimes it's just minor geometric variations that cause these to not line up correctly. But a little bit of coming in and fixing them after the fact will go a long ways towards getting a really good design out of this. And you'll note right here we have an overlap. That's fine. That means that this area is definitely being accounted for by both this rebar and that rebar. So we may be a little conservative for the design in that area. That's okay by me. Alright, so now that we have all of that set up, let's come into the load combinations, and we're going to get rid of the default load combinations since those don't always cover everything that we need. Instead, we want to generate code-specific load combinations. So if we're using the 2012 IBC for strength, I'm going to come in here and tell it that we're going to do that for roof live load, and I'm going to hit generate, and so you see we get 7 different load combinations. This is more than the number of load combinations that were in here by default, which is why I always recommend generating your own load combinations rather than just using the 4 default ones that RISA Floor comes with. And then we can hit solve on this model. And so what this is going to do now is up on the beam floor, it's going to run through a load attribution for each one of those beams, and it's going to optimize the member sizes for them. So it's going to try out every single different type of steel size to find out what the most optimal size is in terms of code check versus self-weight. And then what it's doing is it's performing a finite element analysis on the 2 concrete slab floors. So it's going to figure out all of the forces and moments within these slabs, and then using these design strips it'll figure out all the rebar that needs to run in each direction within the slab in order to get us a rebar design. It's also considering other things like shear, both one-way and punching shear, as well as deflection in the slab. So we finished up our analysis and we get a couple of warnings. We get that no punching shear check was done for non-concrete columns. In other words, the steel columns that are being supported by the two-way slab we're not getting a punching shear check on. That's fine. And that the slab punching shear checks do not consider slab openings at this time. So this is just a couple of locations where it's saying, hey, you might want to take a closer look with punching shear in case it might control here or there. And so now we can get a look at the design that we've got for this. If I go up to the roof, we can see these were all hot rolled steel beams. Most of these have been designed as W10 by 12 beams. And then if we go back down to the 3rd floor, we can actually get a look at what the design was. So if I take a look at the north-south bars, we can see here, maybe it'll be easier to see if we just take a look at the bottom bars. Here we have 19 number 8 bars at 18 inches on center. Here's 20 number 8s at 18 inches on center. In other words, what I'm seeing from this is that in most places here, a number 8 at 18 inches on center is fine in the slab in this case. And if I come down here to the slab results for the rebar, we can confirm that as well in sort of a tabular form. So we get design for the top and bottom bars for both the north-south and east-west directions. So this is giving us our full concrete two-way slab design. And we can get in further and review some of these slab results and see the unity checks and so on and so forth. Alright, so at this point now we have an initial slab design done and a framing design done within RISA-Floor ES. What do we do next? Well, this was only designed for gravity and we want to get this designed for lateral, so we're going to take it into RISA 3D using the director. So if I come up to the director and go to RISA 3D, we can see here that for the wind load, this has all the information that we entered in RISA Floor. I'm going to hit OK, and now I'm within the RISA 3D model. And in the RISA 3D model, here's those braces that got brought over from Revit. Anytime we have a brace member, that gets brought directly into RISA 3D under Revit. And of course, in RISA 3D, all of the RISA Floor diaphragms are being considered. I can turn on the display of them right here so we can see that they are there, but we just have all the gravity members filtered out so that we're only seeing the lateral members, since that's all we care about within RISA 3D. So in RISA 3D, I'm going to come into the load combination spreadsheet, and I'm going to generate those IBC 2012 strength load combinations for roof live load. So I'll hit generate on there. And then under wind, I'm going to do an X and Z wind with reversible. Now, of course, with a rigid diaphragm, in reality, I would need to do the eccentric and quartering wind loads, but we don't want to spend all the time during this presentation having it run through all that analysis. So now I'll solve a batch and envelope solution, and the program's going in here and doing a finite element analysis and solution for the walls and the members, and it'll give us our code checks on those. And what we may find here after we finish solving is that if I go to the design results spreadsheet, we see that those braces, which are all HSS, are all very oversized. The unity checks are all about 0.1 or less, so they're only about 10% stressed. So this means that we can actually downsize them. I'm going to come to the suggested design spreadsheet, and here we'll see it has some other shapes that it recommends in lieu of the 8x8 tubes that were up there. So we get some savings on this one. So I'm going to hit solve again using suggested shapes. And we're going to hit OK on this, and so now it's going to substitute those recommended shapes in for the tubes and use those for the solution. And once this finishes up, we can double check to make sure that everything works fine. So I'll go back to the design results. None of our code checks exceed 1.0, so we're all set. So now we have a gravity and lateral design done for this building. Next, let's use the director and transfer into RISA Foundation. In RISA Foundation, I want to double check my soil properties here. We have a subgrade modulus, which is something you can pull from a soils report, and an allowable gross bearing stress, which is also coming from a soils report. In this case, let's stick with the 5,000 PSF. We'll assume that we have some pretty decent soil at this site. And so what we have in Foundation now is those slabs that were brought over from Revit. So we can see 2 big foundation mat slabs and 3 spread footings as well. So for the foundation mat slabs, I need to draw some design strips, just like I was doing for the elevated slabs. Now, what we ought to be doing for these, because of the layout, is doing several different design strips per slab, since we really want to capture some more localized forces. But in this case, for the sake of speed, we'll just do a single design strip to get through this. So in practice, doing 1 design strip per slab is not something that I would recommend, but if you're trying to do a Reseller-Revit presentation within an hour, I would strongly recommend it. So we'll click that right around here, and we're going to finish up drawing these design strip polygons on both of these foundation mat slabs. And next we'll get a look at the properties for everything. So let's take a look at these foundation mat slabs. You'll note this one has the opening in it. That's that shaft opening that's appeared to every single floor, and that came over from Revit with the shaft opening. I'm going to come into the Slabs spreadsheet in RISA Foundation, and we're going to take a look at the material that we've got set for this. So here it's concrete cast in place gray. So once again, we're going to change this to that concrete 4000 NW. And then for the slab thickness, the Revit slab thickness was 18 inches. In this case, I want to drop that down to 12 inches. So I'm going to come in here to fill block, and let's try out a 12-inch slab and see if maybe we can get some savings on the foundation in that way. Next, I want to go into the footing definitions. So under footing definitions here, I'm going to come up and see that it's imported these footings from Revit as this definition RevFoot1. For the material, once again, let's go with that concrete 4000 NW. And in here, we do not need to put any of these settings on. They'll be unnecessary. For the footing geometry, for the min and max length, you'll see these are hardwired. Well, that's because the footing in Revit was a 6 foot by 4 foot. But in RISA Foundation, we can actually optimize the footing size. So let's go ahead and have it optimized by setting the maximum length and width to be 12 feet, so that way the program can pick out the ideal size. And then for the thickness, as opposed to doing an optimization, let's see if we can just force that thickness to be 12 inches and have it work. And then I want to come to the Force Square checkbox and uncheck that. Next, I'm going to go to pedestal. So the pedestal in this case would be the concrete slabs which are bearing right down on the footing. And so in that case, we can treat that as a post as opposed to a pedestal. And we're going to set its shape up. Let's assume that that's a 12-inch by 12-inch column. The only thing this is really doing is providing us with a punching shear check to make sure that the column isn't going to punch right through that footing. All right, so with that all set, we have 100 PSF overburden on these footings. We're now ready to perform a solution. So let's go ahead and hit solve. And the program's going to come through now and perform once again an FEA solution. On these mat slabs, it's actually creating a mesh of compression-only springs to represent the soil, and so it's figuring out all that soil bearing, overturning, sliding, as well as rebar, one-way shear, punching shear, and everything else. So we're getting a full design on this one. And then in terms of the footings, it's using a sort of closed form solution that's much faster, that assumes that the footing's a rigid body. And that allows us to get a quick and easy solution for these footings where we can come in and see how they turned out. Alright, so we've got our design at this point for both of the slabs and the footings. So we've now completed a design within RISA Floor, RISA 3D, and RISA Foundation. And that means that we're now ready to head back up into Revit and bring this model back with all the changes that we've made. So that's going to lead us into part 3, completing the first round trip. So within RISA Foundation now, what I want to do is hit save, and that's going to ask me if I want to save the results. And when it does that, it's going to actually save the results for both RISA 3D and RISA Floor as well. And then I'm going to use the Director tool to come back all the way out to RISA Floor. And so within RISA Floor here, now I want to hit File, Export, Autodesk Revit Exchange File. And we want to find that exact same file that we imported from. And so I'm going to just map myself over to there. This is an important step that you always want to be exporting and importing, overwriting this same exchange file, because it's not actually overwriting, but instead what it does is it merges the changes together and ensures that the program is only updating things that have changed. So I'm going to sort of overwrite that file here and say yes in this case. We'll get a message that it exported successfully. And so now at this point I can actually close out of RISA Floor. We're done there. And then I'm going to come back to our Revit model. And in the Revit model, under the Add-ins tab, I'm going to go to Import from RISA. Now let's take a look at some of the options that are available here. Well, under the General tab here, you can see the same Project Base Point and Project North. These were options on the export as well, and this just controls how the coordinate systems are aligned between the Revit model and the RISA model. Now under the import process, you see we have a couple of options here. Update the geometry and sizes of the members, or just update member sizes only. So let's say that we maybe made some geometric changes in the RISA Floor model just to make it more accurate or solve faster, but that we don't want the actual physical model of the Revit model to be altered at all. Well, that's a situation where we might want to use this update member sizes only. But in this case, we want to make sure the geometry and the member sizes of the structure are synced up between RISA and Revit, so I'm going to choose that first option there. Now under Elements to link with RISA, we want to bring over the walls and diaphragms, boundary conditions and footings, the beam end reactions, and let's assume that we don't need to do any scaling or rounding on those. Project grids, yes. The loads and load combinations I don't want to bring over back into Revit. I have no real need to do them, and as was mentioned before, if you don't have a particular reason to bring them back and forth, we don't recommend round tripping those. And then the concrete column rebar. So currently the rebar can be exported from RISA 3D and RISA Floor into Revit for concrete columns. And that's also going to be expanding so that the slab rebar and beam rebar can also be brought over as well in future versions. Now under the foundation slabs and elevated slabs, we have both of those checked. And I'm going to come down to presentations and just take a look here under exchange file to make sure that I've still got that same exchange file selected, which I do. So we're good there. And under the Advanced tab, you'll see there's a merge tolerance. You can see that we want to import only the changed items, and there's a couple more advanced features that I'm going to leave alone here. We don't need to use them in this case. So now I'll hit OK. And so what we're getting now is a progress bar in Revit showing us how the RISA-Revit Link is bringing that RISA model now back into Revit. And so it's going to take a look at everything that changed between when we exported from Revit out to RISA and now came back. So it's tracked all those changes, and it's only making those changes in the Revit model without modifying anything else. So this import here is going to take just a little bit of time, especially if we've made a lot of changes. And in this case, we certainly did. We resized basically all of the steel. We resized the foundations, the concrete columns. I think the only thing that really didn't change was the two-way slab thickness or that shaft opening. So we can expect a little bit of time spent just running through here. And this is just Revit making sure that everything is thoroughly connected to everything else. Now, once this import completes, then we're going to get a report that's going to explain to us whether there are any problems bringing it in. And I'll bet that we're going to get a warning that says that the alignment is slightly off on a few members. Now, you'll get that warning almost every time you import from RISA to Revit, and that's due to the fact that the programs have two different tolerances. That goes back to what we originally discussed. So right here, here's our report. We see that all of the 111 beams were modified, 56 columns, 6 braces. So we've got modifications all over the place in this model, and it's going to color code them. But before it finishes the rendering and the color coding, we get this. Beam or brace is slightly off axis and may cause inaccuracies. So I was talking about this a moment ago. This warning relates to the fact that in Revit, everything is all set to the nearest 1/256th of an inch. Whereas in RISA, we take everything about to the nearest 1/8 inch. So what this is saying is that there's certain nodes that may have shifted slightly between going from RISA to Revit that will have shifted by less than 1/8 of an inch. So that's really what this warning means, and so it's perfectly fine to just hit OK on there. It's not going to be harming anything. And so now we get the color-coded model showing what's changed versus what hasn't. And since basically everything was modified, it's all showing up as yellow. But elements that weren't modified come in as black, and any new elements that were added would come in as green. And then if we had any shapes that it wasn't able to translate using the mapping file, those would actually be coming in as purple shapes in this case. So now that we're in Revit, let's go ahead and take a look at what got brought over from RISA. So if I go to my roof plan up here, I can take a look at any of these beams, and if I click on them, I can see the member size that came over. And what I actually want to do here is come up under Insert, and I'm going to say Load Family. And we're going to go ahead and load in the Revit, the RISA tags for all the member sizes and the end reactions and the such. So I'm going to come up here to the Documents folder. And in this case, I'm going to go to the RISA folder. So under Documents RISA, I have a Revit Link 2016 folder. I'll go in there and go to the beam tags, and I'm going to just go ahead and load all of these beam tags into Revit. And that was through the Insert tab, Load Family. So with all those tags loaded in, I can now go to the Annotate tab, and we can come up here to Beam Annotations. And under Beam Annotations here, I'm going to tell it that I want to annotate all the beams with the beam size at the top, with nothing on the bottom, and then at the start end, I want the RISA start reactions, and at the end end, we want the RISA end reactions. And I'll hit OK with that. And what that does is tags all of these beams now in this view, so we can see there's a W10x12 with a 3-kip end reaction. So this is really useful for putting onto your drawings and the such. Now if we go down to the third floor or the second floor, you'll note there's not really anything shown in here. It's not currently bringing the rebar back and forth between RISA and Revit for the slabs, although that eventually will be possible. But what we can see is that it did bring the rebar over for the columns. And this is something that might be useful to show on our plan views. So let's go ahead and set up a drawing in Revit so that way we can actually have this information be used for something useful. So in Revit, I'm going to come into this view here for the second floor, and I'm going to shut off the display of elevations. I'm going to zoom in on this column right here, and under View, I'm going to set up what's called a Callout View from Revit. And so if I just set up that callout right there, we can drag this bubble up here and get this to look correctly on the drawings. And then I'm also going to set up a section view on this column. So we come up here and draw this section, and I'm going to pull that back as well. So if I double click on the callout here, we come into this view, and I just need to do a couple things to make it look good for the drawings. So one thing I want to do is shut off the display of the grids and of the section cut as well. And this is just using the Revit visibility options. And then in Revit here, I want to come in and turn off the crop region. Now we want to set an appropriate scale for this one. So let's do an 1.5 to a foot scale and set this up as a fine detail level with wireframe. So what we see now is this is the stirrups and the rebar for that column that were brought over from RISA. And these were actually brought over as individual elements. So we can see right here, that's a rebar bar number 7. This is a rebar bar number 4 stirrup. And I can actually tag these in here. So if I go up here to, once again, insert load family, I've got my own custom rebar tag that I've got set up. And so if I go to annotate and say tag by category, I can actually come in here and tag this piece of rebar. And I will drag the tag over to here. And we will set this up as the type that was pre-set up. So here I can call out that rebar as a number 7 rebar. And then I can also do things like show the cover. So maybe I want to show that I've got an 1.5 clear cover all the way around that stirrup on here for this drawing. So next I'll go back to the second floor and let me double click on this section. And so now we get the section cut for that column. And let's take a look at that column maybe just between the second floor and the ground. So I'm going to bring this up. Once again, I'll come back in here and I'm going to turn off the display of the grids for this view. And we're going to turn off the display of the crop region. And then for this view, we might be better off going with a scale of, say, 3/8 to a foot. And I'll pull the levels out just a little bit so we can see closer in here. I'm going to once again crank up the detail all the way to fine. And so what we see is there's the column with the longitudinal bars. There's the stirrups that were brought in from RISA. So these were based off of the RISA concrete column design. And we can see in here that there's 13 of these at a 1'2" spacing, and the shape type is a T1 within Revit. So I'm going to come under Annotate here within Revit, and we have the multi-rebar annotation. So I'll come in here and say I'm going to do a linear multi-rebar annotation. I'll click on those rebars, and then I'll bring it out to this side, and then let's just put the label right out here. And I've always felt that this other type of rebar annotation, that's just called structural rebar, looks a little better within Revit. So I'm going to flip it over to that. And so this shows a call out right in here. So Revit recognizes that that's 13 number 4 bars at 1'2" on center, and that we have 12 spaces between them at 1'2" on center. So this is a great way to take the rebar design from RISA and bring it into Revit and actually use it on a real project. So now that we've got that set up, let's go ahead and create a sheet in this case. And so within Revit, for those of you who haven't used Revit before much or aren't familiar with why Revit's so handy, it's mainly useful for construction documentation. Because what I can do now is I had this RISA model, and I can now actually just drag the second floor plan from the RISA model onto this page here. And I can take these other details that I set up, such as that column size and such as that cross section that we had set up, and I can drop those right onto this drawing. And so what we've got now is this is drawing number S1, And so here's my second floor plan view, and we can see there's a call out, and it automatically labels what sheet these are on and what detail numbers these are. And then I can come over to say detail number 2 on here, and this is the call out. And so this is all live information that's come right from my RISA model without me having to do any sort of CAD line work whatsoever. So it really makes it very nice and convenient. And of course this information gets updated as we go back and forth. So we can take a look at that. Now before we go back into RISA for our second round trip, let's say that there's been some changes made by the architect. And so we're going to come in here now to the elevations, and what I want to do is actually move this ground floor down. And so we're going to say instead of the ground floor being at -2 feet, we'll say it goes all the way down to -6 feet. And so that's going to scoot everything down. It's going to make these columns taller. It's going to make the wall taller. Now you'll note that the windows all got pulled down in the wall with that, but of course we don't want those down there. So I'm going to go ahead and reset their base offset to scoot them back up to where they were, so that those windows are back up correctly now at this floor. And then the other thing that we want to do, let me just set that 2 foot right in there, is these openings right here got taller, and I'll just assume maybe they did get taller as part of this whole building getting taller. So we'll leave them there like that. The other change that we want to make is to come in here and change that shaft opening. So I'm going to click on the shaft opening, and you'll note in the 3D view that that opening extends all the way down through the foundation, second, and third floors. And so if I click on this opening and say Edit Sketch, let's make this a different shape here. And so this would be a very normal thing in a project to have an extra change in the way that the shaft openings are done. I'm going to select that, and then we'll click on the shaft opening, and I'm going to copy that over to the other side of the building as well. So maybe we added a second shaft in this case. And so I'll just drop that right in there. So now we have 2 L-shaped shafts in this building. And so with that all set, we're now ready to move on to the next part. And that will be exporting the changes to RISA Floor. So within the Revit model, what I'm going to do is come up to the Add-ins tab, and once again say Export to RISA. I'm going to make sure that we're pointing to the correct model, and this would be the Exchange file in the model that we were working with before. I want to double check that all my settings on here are the way that I want them, and then I'll hit OK. And so once again, we will get an export back out to RISA Floor so that we can continue working on this structure. Now you'll note that went pretty quick, and here we get our export report. And so I'm going to hit OK, and now RISA Floor is loading up, bringing in just the changes that we made since the last time we were in RISA Floor. So things like the fact that that floor-to-floor height changed, or that we added that extra opening or changed the shape of the openings will be brought over, but most of the properties in the RISA Floor model are kept as they were. So for example, you'll note that those beams and columns that we changed to be lateral in red there did get brought over as lateral. So I'm going to make a couple other changes as well. Let's say that in addition to the fact that we increased the floor-to-floor height and that we changed those shaft openings, that we also are going to have heavier loads on this building. Well, I'm going to come into the Area Loads Definitions spreadsheet, and under here, under the roof load, let's say we're going from 10 PSF up to 15, and from 30 PSF live up to 30, or from 20 to 30. And then let's also say that the other floors, the second and third, rather than being an office load with 50 PSF of live load, will now be a storage load with 125 PSF of live load. So we should see things bump up quite a bit due to these changes. I'm going to come over here under the floors spreadsheet and change the area load for the office to be storage for both of these. And that'll be for the second floor and the third floor. And then up here on the roof, we're going to stick with that same roof load that we had on there before. So now I'm going to hit Solve in RISA Floor. Now when we exported from Revit, if I duck back here for a second, you'll note that we had the Optimize Member Sizes option chosen, which means that now within RISA Floor, it's going to re-optimize all these member sizes based off of what we had before. But alternatively, we could have just told RISA Floor to reanalyze those same sizes that we had before, in which case we would now be getting warnings telling us if anything that had previously worked now didn't work. So that would be also helpful if we had, say, already submitted initial sizes and we were in a later part of the design where we really didn't want to resize anything. We just want to make sure that everything will still work with whatever changes were made. So now that that's done, we can see that some of these beams have now been bumped up. If you recall, before these were W10 by 12s, now we have W8 by 18s. So we're getting a little heavier beams up on the roof there due to that added load. And if I come down to the second floor, the third floor here, we can see some of our designs as well. And if we come in here and take a look at, say, the north-south bottom bars, most of these bars are looking pretty similar to what they were before, the number 8's at 18. So it appears that that didn't impact things in a huge way. And let's just take a quick look at what the displacement is. I can come in here and take a look at a color-coded displacement to see that nothing's going to be sagging too much. And so what we can see right here is that on this slab, we've got about 1 inch of deflection way out at the tip of this cantilever. So we'd have to determine whether or not that was a acceptable amount of deflection due to the amount of loads that are going to be put on there for this new storage load that we've put in. All right. Now that we've got our gravity redesign done, we're going to use the director and go back into RISA 3D. And in RISA 3D here, we've got the same situation. All those load combinations we had set up before were just fine. I'm going to go ahead and resolve the model here. So we're going to do that batch and envelope solution. And it's going to run through now all the wind load cases, except of course for the eccentric and quartering, which we omitted in this case, but which normally you would want to have. And so with that solved now at this point, let's take a look at the design results. None of the braces that we had before failed, so we're in good shape there. So we'll actually leave the braces alone and we won't resize them. And then I'm going to use the director to go into RISA Foundation. So in RISA Foundation, let's just take a look real quick in the footing definitions. And so you'll see because we had two different footings sized when we went out to Revit before, it created them as two different footing sizes in Revit. So when we come back into RISA, now we have two different footing definitions created here. And so we can actually check to see whether these footings are going to work because we have the sizes hard-coded right in there. So I'm going to go ahead and solve the model in RISA Foundation here. And we can see also there's those shaft openings coming down into the foundation slabs. Now before I solve it, actually, I do want to go back in and do one thing. The RISA Foundation default load combinations are set up without the live load storage, the LLS, or this is also known as live load special. I want to make sure those are included. Of course, just like in RISA Floor and RISA 3D, where I mentioned earlier, it's best to generate your own load combinations. I would always recommend doing that in RISA Foundation as well, because the two default load combinations may not capture all the categories that you need. So of course RISA can't determine everything for you automatically. It's always important to review all that input, especially things like load combinations, very carefully and putting your engineering judgment onto that, because the last thing that we want in this situation is a garbage in, garbage out scenario where we ignored a certain load combination because we thought the program had automatically done that for us. So now RISA Foundation is getting through its solution right now, and we're going to see whether or not those existing footings will still work with the new loads. And so what we've actually gotten now is that we can see these footings have been resized. There's actually a different size being assigned to them. And so I can take a look, say, at a detail report for one of these footings to see what we have here, or maybe under the footing results, and take a look at the geometry. Now one thing that I'm noticing here is that these have been sort of resized as square, and so what I suspect happened is that force square box got checked. I'm going to uncheck that and just rerun another solution real quick. And so these right now were set with a maximum length of 7 and 8, so I'm going to allow this to once again go all the way up to 12. So let's resize these footings. I'll hit solve on this, and now it's running through its solution. And we're going to see what it comes up with for an optimum footing size. And once it finishes this, then we'll be able to bring those back into Revit, and we'll have the correct footing size that we actually need. And so it's nearly finished optimizing through all these. We can see there's only 2 load combinations in this case, so it goes rather quickly. And once that wraps up, we will have our footing designs. And so we can see the footings are a little bit different size than they were before. I just had to uncheck that force square so that it wasn't trying to force them into a square size, because in this case we wanted to have them as a rectangular size. So now we're done in RISA Foundation. I'm going to hit Save and save results once again. And then using the director, I will back all the way out to RISA Floor, and we'll hit Save, Save Results. I'm going to go up to File, Export, Autodesk Revit Exchange File, and let's take this over under Presentations here and put it on that exact same Exchange file that we've been working with time and time again. So I hit Save on that, hit Save once again, and so then this means that now we're going to be moving on to our next portion, completing the second round trip. To do that, once I've saved everything in RISA Floor, I can then close out of RISA Floor and pull open the Revit model yet again, and under Add-ins, we're going to go to Import from RISA, make sure that all the settings are still the same way that we want them, and I'm going to hit OK. And what we should see is that we didn't make as many changes between the last import as we did between the first import. So therefore, this whole process should go just a little bit quicker than it did the first time around. And of course, if we'd made almost no changes, like let's say only resized one beam, this whole process would only take probably about 10 seconds to get through, because this is only going to be updating anything that's explicitly changed. But even so, because most of this information is here, this all should go rather quickly. And so what you can see with the progress bar coming along here is that it's making these updates. In the case of layout 1 and 2, that's talking about each floor plan that it's going through and updating. We'll get the color-coded changes, and of course we know what to expect in those color-coded changes, that being that many of the beam and column sizes changed, but we didn't make any changes to the sizes in the braces in this case. So I've hit OK on that one. And now it's just updating. We'll probably get another message about the other elements not being affected, and there we go. So now we've got our complete round trip in this case coming over into here. The next thing that I'm going to come and do in this case is go into that sheet that we had drawn. So let's go back into the sheet, and so we can see now with this column that now we've gone up to 9 rebars instead of 4 rebars around this column for the longitudinal bars, and that's because we upsized the height of the column and the forces on it, and we can see that in here as well. And so this is a really handy way to make changes and go back and forth between RISA and Revit and keep both of your models synced up, and you can see the usefulness of this for rebar. Now, in addition to the ability to graphically display the rebar in 3D and of course in these 2D section cuts, Revit also has rebar scheduling capabilities, and so you can actually put together rebar schedules that will have all the information that's in there. And for more information on that, you can contact Autodesk to find out how the best way to put together a rebar schedule for your model that was imported from RISA was.